Okay, I say it's 1:21, we're over. So let's get started. Announcements, just real quick. So homework 4 was due today. Hope you got that in. And homework 5 was scheduled for Friday. Once again, I've pushed it back to Monday. Most of these lessons we've done so far have taken about 2 weeks to get through the material. And actually, all 4 of them, lessons 1, 2, 3, and 4, were all 2-week lessons. Lesson 6 will also be a 2-week lesson, but 5, 7, 8, and 9 are faster paced, just 1-week lessons. But still, I think I'll need a full week to get through this material. So plan on that on Monday. Okay, let's do a pair of warm-up questions because I assigned you 2 videos, and so these will be tied to those 2 videos. The first was a short video on interferometry, which I mentioned briefly, but didn't have time to explain how it works in class. But this is another resolving power calculation, just not with a single telescope, but with an array of telescopes hooked up as an interferometer. This is the Very Large Array in New Mexico, built in the 70s. It's been a staple of radio astronomy since then. Consists of 27 25-meter diameter telescopes, and they can be spread out over different baselines. But when they're spread out over 1,000 meters, so a kilometer, you can stretch them out such that the diameter of the distribution is 1,000 meters. And suppose it's observing 0.7 centimeter light. That I think is probably as small of a wavelength as it can do. What is the resolving power or the blurring scale of this interferometer? And so we use the same equation. In fact, I gave you another version of it that's useful for radio telescopes because it's already in centimeters for the wavelength. What comes out is in arc minutes, which you may have to convert because this is looking for the answer in arc seconds. Well, I'll give you a little bit of time, give you maybe another half minute or so.
Dr. Reichert.
Yes.
In the equation, do we derive the centimeter light to wavelength?
The wavelength is given in the question, 0.7 centimeter light. That means that's the wavelength.
Okay.
Looks like I have about 120 of you today. So let's see if we can't get it up to 50. or 45. There we go. Okay, let's see what this looks like. Yep, most of you got the right answer, 1.7. Add some bins, may see some other structures. Yep, this right here. So most of you answered 1.7 or 1.8, and there's another little bump around 0.028, which I think I can also explain. So let's take a look at the answer. So here's the resolving power equation. This is the version for radio telescopes. The other one begins with 0.25 arc seconds, but they're the same equation. This one uses arc minutes in centimeters. The other one uses arc seconds and microns. So whichever makes more sense. I think in this case, this makes more sense because the wavelength is given in centimeters, 0.7. The diameter is given in meters, 1,000. And so you just enter those numbers. And you'll have 40 arc minutes times 0.7 divided by 1,000. That gives you 0.028 arc minutes. That explains our secondary peak over here. But again, that's in arc minutes. And normally with radio telescopes, or at least single dish radio telescopes, that's a good unit. But these interferometers, they're able to achieve much better resolution because the very huge diameters. So you'll want to convert that into arc seconds. And you do that by multiplying by 60, which gives us the 1.7, which in the bin here, there it is, 1.7. Okay, and that's getting pretty close to what we see at visible wavelengths given atmospheric blurring. Of course, this is not atmospheric blurring. This is the resolving power of the telescope. As we pointed out, radio telescopes are notoriously bad because the wavelengths are so huge. And now we're getting up to such large diameters, it's compensating to a large degree. So the picture you'd make with this would be comparable to a ground-based visible light picture. And of course, you can have bigger interferometers as well, and ones that work at shorter wavelengths. So you can do even better than this. Okay, as the first one. The second one's not calculational. So I assigned two videos. One was on interferometers, and the other was on space-based astronomy. That was a longer video. And we went through, these are the telescopes that we discussed. Oops, 1 second. Clear the question. In this video, Spitzer, Hubble, Webb, Chandra, Newton, Compton, Swift, and Fermi. And I think I've ordered them from long wavelength to short wavelength, low frequency to high frequency. So if you didn't get a chance to watch that video, you'll want to, because any of these telescopes are fair game. We spent a lot of time talking about visible light astronomy and some time talking about radio astronomy, but there's still a whole bunch to the electromagnetic spectrum that all of it has to be done from space because it doesn't make it through the atmosphere. And so I dabble, I basically present the key spacecraft, the key telescopes in each of those regimes. So I want you to know them and understand them. So here I'm asking a specific question. Which of these make use of a coated aperture mask? And you can pick multiple. Just append the numbers and submit it as a combination.
Dr. Reichart,
Yes.
do we have class on Friday?
Why would we not?
They sent out an email that said that they were recommending teachers not have class for in recognition of Mental Health Day.
I'll take a look, but I can't make any promises.
Okay, just
Yeah.
thought I'd ask.
But if the university has done something like that, if I choose to have class, you don't have to attend. You can always watch by video. But I'll take a look and see what the university is proposing. The thing is, whenever they say we can take time off, because of the state regulations, we have to make it up at some point as well for accreditation purposes. So again, I haven't seen that. I'll take a look. But if they say we can take the time off, great. But it means I just have to schedule a makeup class, in which case I may just video it and you don't even have to show, but you'll have to watch the video. But again, I'll check out the details before I could say too much. It does seem like a good idea. We could all use a mental health day off.
Did you say this list is from longest to shortest wavelength?
It is, yep. For the most part. I mean, there's some ties in there. Where there are ties, I think they're listed chronologically. It's also the order I presented them in the video. I'm going to cut off there. We have smaller number. This is an easier question because it's not calculational, but it is dependent on whether you watch the video. And this suggests to me that maybe some of you still need to watch the video because we're getting a lower response rate. That's okay. That's why I'm throwing these up here to encourage you / scare you into watching the video before the next exam anyway. But yeah, in the homework, I asked you about which telescopes, it was something like which telescopes use nested barrels of mirrors. So this gives me an opportunity to review just a little bit of that. This is separate from the warm-up question, but tied to the homework question. As you go up to higher and higher frequencies, shorter and shorter wavelengths, the nature of the telescopes changes. And it's because the photons are getting more and more energetic. And instead of bouncing off the mirror, they'll go right into it and embed into the mirror. And then you can't make an image if your photon gets stuck in your glass. So as we go to higher frequencies, they have to change the design. In the homework, I asked you about these nested barrels. We use these with X-ray telescopes. So not as energetic as a gamma ray, but still pretty energetic. It can penetrate your skin, but not your bones. That's why doctors use it to image fractures. So the way they get those to focus into an image is they skip them. They don't bounce directly off a mirror like a visible light telescope. They come in at a glancing angle. They come in at this side, get into one of these openings, and then you have maybe one or two reflections, gentle reflections. It's like a stone skipping off water. If I take a stone and just throw it down into the water, it sinks. But if I spin it and skip it at a glancing angle, it can bounce. And X-rays, you can still bounce them if you're at that glancing angle. And you'll see that with telescopes like Chandra and Newton, which are the US and European X-ray spacecraft. Now this question takes us to even higher energies, into the gamma rays. And at these energies, you just can't bounce them. So instead, they make use of something called a coated aperture mask. And here's an example of one that they put over the front of the spacecraft. And it's a unique pattern. There's no part of it that replicates. And it blocks half the light. You lose half your gamma ray light, but the rest comes down and casts a shadow on your detector. It's like a CCD essentially. And you look at the shadow and say, oh, I recognize that pattern. That pattern corresponds to this part of the coated aperture mask. And so you can establish an angle and figure out where the light came from. So in this way, you can have some directional information for your incoming light and reconstruct a picture. And so that applies to these two here, Swift and Fermi. Compton was the original gamma ray spacecraft. It had a different approach. You can watch the video for that. But modern day gamma ray spacecraft, such as Swift and Fermi, make use of that coated aperture mask. So I've given you the answer. I can see these are, with these combination ones, it can be challenging. We got a 7-8 here, a 7-8 there. I see a lot of sevens. So you pick that up with Swift. There's a 7-8, but it also applies to Fermi. There's an 8 there. I mean, I could do a histogram, but it's just going to be well, not that bad. We got a 7 here and a 7-8. So most of you are kind of on track. Okay, cool. All right, so we are now into lesson 5. And I think there'll be fewer video assignments. So I think I have viewer videos prepared. So we just got to get it right now and stay on target. Okay, so lesson 5. And we are getting back to the solar system, finally, after this time. I said we're going to take a little pause and learn a little bit about the nature of light in lesson 3 and the instruments that we use to detect light of all wavelengths in lesson 4. So now we have a bit of a toolkit that we can come back to the solar system with greater skills, greater abilities. And this is really important before we tackle each planet individually. In lessons 1 and 2, we learned the basics kind of their motion, that they're out there. In lesson 1, we learned about the sun, the earth, and the moon and their motions. In lesson 2, we introduced the planets and their motions, but we really haven't spent any time studying the objects themselves. What are, even their bulk properties. How big are they? What are their masses, their densities, their likely compositions, let alone the details of surface features and weather phenomena and the moons that go around them too. So that's where we're going now with the rest of the course. In lesson 5, we're going to talk about kind of 2 things, the discovery and the exploration. There we go, exploration of the solar system. And this is meant to be introductory, to welcome you back to the topic. Today we'll take a historical approach. I'm getting a phone call, but I can't take that right now. Turn the buzzer off. We'll take a historical approach because that's fun today, and then we'll get into some calculational stuff. In particular, the homework 5, is different from all the homeworks. I don't know if you've looked at it yet, but it's different from all the other homeworks in the course. This is essentially a single problem broken down into more manageable pieces. The problem of what happens when we discover a new point of light out there moving across the sky. So it's some kind of planet or dwarf planet or something orbiting the sun. How do we figure out these things? How do we figure out how big it is, how massive it is, density, likely composition, these bulk properties? You see all this stuff in tables in the textbook. Where do these numbers come from? And so we'll spend some time, basically the flow is I'm going to discuss the discovery of the solar system from a historical point of view, and that's just low-key story time stuff. And then we'll spend the better part of a class talking about how to do homework 5, because it's all calculational and each problem builds off the previous one, which sounds scary and intimidating, because what if you get one wrong early on? But they are multiple choice, so you'll actually run out of answers if you go too far down the wrong path, and that will tell you to go back. Anyway, I want to spend a whole class helping you on the math to do this homework. Then we'll talk about the exploration of the solar system, meaning primarily spacecraft exploration. So that's lesson 5. Let me just also briefly overview what's coming after that. In lesson 6, we'll focus on the Earth and the Moon. We're going to take this approach called comparative planetology. So as we talk about the other planets farther out, we want to compare them back to planets and moons that we know really well. And of course, we know the Earth really well, and we know the moon pretty well, and we've been there, of course. And so we'll spend all of lesson 6 setting up those 2 objects for this comparison exercise. And then in lesson 7, we'll talk about the terrestrial worlds, terra meaning Earth, so terrestrial meaning Earth-like, and those would be Mercury, Venus, and Mars. And of course, the Earth and the Moon are terrestrial as well. But we'll compare Earth, Venus, and Mars back to the Earth and the Moon. In lesson 8, we'll tackle the Jovian or Jupiter-like planets. Those are the gas giants, the 4 gas giants. and we'll compare and contrast them to the terrestrial worlds. They're very different. And as we're going through the Jovian worlds, we'll talk about their large moons. Overall in the solar system, there are 7 large moons, moons that are large enough that if they weren't going around planets, if they were instead going around the sun, we would call them planets. One is our moon, and the other 6 orbit the gas giants. And so we'll spend some time on them. We'll also touch on a few other moons out there that are interesting, but the focus will be on them, and the rings out there as well. And then in lesson 9, the final lesson of the course, which we'll do in the final week, it's kind of a catch-all, but it's primarily going to be a synthesis piece. By that point, we will have learned a lot of information about the planets. Can we describe how it all formed in simple terms? A few simple concepts to explain how the solar system got to the way it is today. And even amongst the planets, you'll see, and the moons, you'll see tremendous variation. And it's not going to be about, I want you to learn these 10 facts about Jupiter and 15 facts about Saturn. I'm going to try to boil it down to 2 or 3 basic physical concepts that can be used to explain the tremendous diversity that we see in the solar system. But lesson 9, we'll try to explain how it came to be from just a few basic concepts. And we'll also venture outside of our solar system briefly and talk about all the planets we're discovering around other stars. We now have that technological capability. Okay, so that's the flow for the rest of the course. Let's jump back into our reintroduction to the solar system, focusing on the discovery today. And if we have time, we'll start working on the math to help you through the homework. But let's start by listing the objects in the solar system in their order of discovery. Well, so we're going to take this chronologically. So let's start with prehistory. Before written history, what objects were known? It's a short list for objects in the solar system. The first object in the solar system discovered, anyone want to guess what that might have been?
Sun.
Probably even before that.
Earth.
Earth, yeah. We probably realized the Earth was here first. But after that, yeah, the sun and, of course, the moon. And then after that, they probably noticed the stars, but I'm not considering them solar system objects. So what would our next class of objects be?
Jupiter?
Other planets. And I was going to ask you to list which planets were known all the way back in prehistory. So I heard Jupiter, that's one of them. What else?
Venus, Mars, Mercury.
I heard Venus, Mars, I heard Mercury, and what else?
Saturn.
Saturn. And that's it. All the others require telescopic aid. So they didn't have that back then. These are the 5 planets. Of course, Earth as well. But we've spent a lot of time talking about how the ancient Greeks didn't consider that a planet, but I'm just trying to get everything listed. And then you have, actually, let me put up some figures here. Let's see, I've gone into lesson 4 directory, so let me go into lesson 5 directory. Okay, so discovery of the solar system, prehistory. So there are the 5 naked eye planets: Mercury, Venus, Mars, Saturn, Jupiter. Mercury, it's really close to the sun. It's hard to see. I have seen it, but not until only a few years ago when I made a concerted effort to go out and find it. When I knew it was at its greatest elongation from the sun had just set. I waited for the sky to get dark enough and I can get just a little bit of Mercury before it set too. So I have confirmed it does exist. It is out there, but it's not one you naturally see. But the other 4 are popping up all the time. I like this figure because they're all on the same side of the sky. And that happens every couple decades. You'll get them all kind of clustered, just chance. And then you see all the crazy stories out there, people who believe, I'm getting some background sounds, let me mute a few of you. People who believe that they will, if all the planets are on one side, they'll pull Earth out of its orbit and it's impending doom. But this happens again every couple decades, and we've been around for a long time. So if you see that kind of stuff, just chuckle, don't take it too seriously. They do have gravitational impact, but they're very far away, and it doesn't really impact our orbit that much.
I have a question.
Yeah, go ahead.
So what would be Earth's impending doom? like the sun exploding, or would something else happen before that?
Yeah, I mean, there's always the chance of a big asteroid impact. And we'll spend some time on, I think, the last day of class or the second last day talking about that kind of stuff. Uh, we get hit by asteroids all the time. And most of them burn up in the atmosphere. The bigger ones can make it through. And sometimes you have really big ones that can cause a mass extinction. That's every like 20 or 30 million years. But that doesn't destroy Earth. Life comes back. And now we have technology. We'll probably see something like that coming and prevent it. There are different ways we can prevent it given the technology we just barely have these days. But some things that we can't control, the sun, it does get more luminous with time. As it's burning through its hydrogen, producing helium in the core, it's changing the structure, getting bigger and more luminous. So in about 3 billion, the sun has about 5 billion more years of fuel left, but after about 3 billion years, it's not going to really be habitable here anymore. It get too warm, the water will boil off, and as it starts to evaporate, it's kind of a runaway effect. It gets in the atmosphere. It's a greenhouse gas, the most potent greenhouse gas, not a man-made one, a natural one, but the most potent. And so that causes it to kind of run away, and we'll lose our oceans in about 3 billion years. And eventually, in about 5 billion years, the sun will come to the end of its life. It won't explode. The core will collapse. The outer layers will expand, engulfing the Earth. And Earth will be orbiting within the sun, which I haven't worked through the math, but it can't be good for our health. And it's also a source of friction. Our orbit will probably decay and fall into the core. But 3 billion years is a long time. Hopefully we'll develop the technology to travel between the stars by then. I know that sounds like crazy, far future science fiction, but once we've mastered the fusion problem, our energy sources, we have all, we use fossil fuels and all sorts of things. In terms of nuclear fuel, we use fission, which is breaking apart plutonium, uranium, messy stuff. But we're also trying to figure out how to do fusion. We do know how to do it in an uncontrolled way. Our nuclear bombs are fusion bombs these days. The initial ones were fission. But if we can control fusion, run it in a sustainable way, basically reproduce what's going on in the inside of the stars, it gives us an essentially infinite power source. And the fuel is hydrogen, or isotopes thereof, the most abundant stuff in the universe. So, everything changes once we have controllable fusion. And there are large efforts underway to master this. It'll probably take a century or two. The joke in fusion is we're only 30 years away, but they say that like every 30 years. They say we're only 30 years away. And so who knows when we'll actually pull it off. But that's, what's it called? I forgot the economic term, but a society without financial needs or pressures, post-something society. But that's what it will be. Once we master fusion, it's free energy, and we can do anything, including long-winded, but here I come around to the initial point, including venturing to the nearest stars.
So like all the funding, when we put it into space exploration, like could actually end up like saving us from like just completely being removed from Earth.
Oh yeah, again, 3 billion years is a long time. We'll probably be traveling to the stars in a couple hundred years, which is nothing if you think about it compared to how long we've been here. We're right on the cusp of that technological capability. So yeah, it'll save us with billions of years to spare. And people have done calculations how long it takes to colonize the Milky Way, like all the habitable systems. The galaxy's huge. And it's about 30 million years, but that's also nothing. That's 1 or 2 evolutionary timescales. The Earth has been here 4.5 billion years. 30 million years, that's 0.3 billion years. We'll have the whole galaxy colonized. So, step 1 is get that fusion and knowing how to do it efficiently, economically, and then we can begin this journey. And yeah, when the sun wipes out the Earth, it's not a problem because we'll be scattered across billions of other worlds by then.
Okay, cool. That makes me think about the future way more positively.
Yeah. We're at this critical point in our history where we're on a single planet. We have filled it up essentially over the past generation, really. If you look at population as a function of time, you go back just a little and it was low, and it has skyrocketed, largely due to science being able to provide food more easily and cure disease. But we're about to fill up the planet. In your lifetime, we'll probably hit the maximum sustainable amount. And so we're in a very dangerous situation where we've maxed out our planet. We're pushing its resources to the limit. You all know everything about climate change, and you've heard all this. But again, we're only a couple hundred years away from, and we'll start by zipping around our solar system and setting up other places, but there's no comparable place in our solar system. Mars is a tiny, half-gravity, atmosphereless, cold, geologically dead rock. It's not really the great future destination for humanity, but we'll practice there and eventually go farther out. Okay, so that was a diversion, but it was a fun one. Yeah, go
I
ahead.
actually have a quick question regarding this. So, like, if nuclear fusion becomes possible within the near future, how are we going to guarantee that it's free? Because, like, for instance, like, fossil fuels have been around for about a century or so and being used and been monopolized by big corporations. Who's to say when nuclear fusion is discovered that it won't be controlled by, again, these same companies, and energy won't be going to be expensive, and it's going to possibly even wreck the world, used for wars and such?
Yeah, the question is who will control it? Because it's not just hydrogen and helium that are the fuel sources. It's isotopes, kind of rare isotopes. Initially, we'd have to scrape it out of the lunar soil. That's where we have the biggest nearby deposit. And eventually, we'd want to pull it out of the gas giants. The nice thing is, we have these gas giants in the outer solar system. I know it sounds very sci-fi futuristic, but think of where we were technologically 200 years ago and compare that to today. So go 200 years in the future. Yeah, you can imagine atmospheric mining operations of the gas giants extracting all the fuel you'll ever need. But yeah, the question is who will have the capability of doing this? And, initially only a few will, but these are big planets. It's hard to monopolize an entire gas giant's atmosphere. So anyone with the resources to extract these things will then have tremendous energy supply. I mean, energy will become dirt cheap, even if you only have a few corporations. Just unless they're colluding, it becomes dirt cheap once you develop the technology to get the fuel sources back to Earth. But I hear your concern, and I'm sure it will be an issue for a while. All right, but back to the solar system, or the history of the discovery of the solar system. So yeah, and we listed pretty much everything. You can also throw in things like comets, as you see here, or meteors in this image here. But back then, I mean, they are solar system objects. They would see them, but back then, at least by Greek times, which is we're getting into written history, they didn't really consider them solar system objects. They considered them atmospheric phenomena. They thought that, as we talked about before, the comets they thought were atmospheric. The meteors actually are atmospheric. This is dust that falls off of comets. As comets go through space, they leave a trail of dust and debris, and Earth will then move into these trails, and the dust burns up in our atmosphere and making little meteors. And that's why they come in showers. As we pass through a tail or a trail left behind a comet, could be from hundreds of years ago, you run into a bunch of them at once and you get meteor showers. Anyway, we'll put those aside. So let's dive into history here. We'll start with the 17th century, which is, of course, the 1600s. Those numbers never match, something to keep in mind. And we already know the beginning of the story with Galileo taking his telescopes, and here they are. I don't think I showed them to you before. 2 telescopes. He made other ones later, I'm sure, but these are his two initial telescopes, which I might have mentioned. We had replicas made of one of these telescopes, and I still have one or two floating around my lab, and they are nearly impossible to use. It's remarkable he was able to do what he did. And we talked about his major discoveries, but here we're talking about discovery of new worlds. And he was the first person to discover new worlds out there. These, of course, being the 4 large moons of Jupiter, the Galilean satellites, which brings our total up to 5 large moons out of the 7 I said are there. So that was, pretty awesome, discovering new worlds for the first time. And of course, going around Jupiter presented a problem for the geocentric model. And that was 1609. I'll give you the dates, but I'm not going to test you on dates. I might ask you if something happened in this century or that century, but I won't ask you for specific years. He also took a look at Saturn. We've talked about his observations of the sun and the moon and Jupiter and Venus. The next brightest thing in the sky is Saturn. And these are images he drew of Saturn. He couldn't quite figure out what was going on, that there are rings around Saturn. At first, he thought there were 2 large moons, so close that they were touching the planet. Later, as his telescopes improved, he almost got it right. It comes across kind of as, handles, coffee mug handles on either side, but he didn't quite get that it's a ring going around the planet. That didn't come until later, 1665. Here's Huygens again. We saw him in the debate with Newton about the nature of light. 1665, he took a look at Saturn, and he wanted to use a bigger telescope. He didn't have one, so he came up with this ingenious arrangement here. Imagine a telescope tube going all the way from his eye all the way up to here, but he didn't have a tube that large, so he just built he built the top of it and the bottom, and put the top up here on this pivot that he could reorient. And then all he has to do, is line up the thing he's looking through such that you end up looking through the front piece of the telescope here, such that you're looking at, in this case, Saturn. Of course, keep in mind that we're on a rotating planet, so Saturn doesn't stay put. It moves across the sky. And it's probably only going to be in this telescope's field of view for a minute, if that. And that doesn't give you long to get everything perfectly lined up. It would have been a very cumbersome process. Then when it's done, you got to rearrange everything and still try to do it. It's hard enough if you're using a telescope that doesn't automatically track, just keeping it in your field of view. This kind of 2-piece arrangement would have been a nightmare. I understand why he has a large pot of coffee. I mean, look at the size of that. It's like, it's about this big. It would have been an all-night endeavor, but on occasion he was able to pull it off. And this is the picture he drew of Saturn. Of course, this is before before cameras, so no recording device, before photographic plates. And so they have to draw it. But he realized, yes, there's a ring going around, and we later will learn that it's multiple rings, but he saw one ring-like structure. He even saw the banded cloud structure of the planet, as you can see here. And he discovered Titan, the large moon of Saturn, which brings us up to 6 of the large moons. Our moon, the 4 Galilean ones called Io, Europa, Ganymede, and Callisto, and you'll get to know them all very well by the end of this course, and Titan. I think that word is Luna, and so I think he's drawing our moon for scale. He didn't quite get it right. Titan is bigger than our moon, but not that much bigger. But still, he discovered it. Okay, that was 1665, discovery of Saturn's ring. And then you have, this is Cassini, who came along, again with the long hair. That was the style back then, I guess. And Cassini, he discovered that the ring actually has a gap in it. He realized the ring is 2 rings. In modern days, we know Saturn's, you can break it down into thousands of little ringlets if you want. but that big ring can actually be broken into two pieces. The division is called the Cassini division. So he did more studies of Saturn's rings, and he discovered many of Saturn's medium-sized moons. Titan is the big one. This is a modern day picture where you can see kind of the double ring, and you can even see cloud patterns on Saturn here. But then you have some medium-sized moons such as Rhea and Tethys and Dione and Iapetus and a few others. He discovered some of those. And that was in the 1670s through the 1680s. That gets us through the 17th century and into the 18th century. 18th century, not much happened until near the end. 1781, you have William Herschel, and he discovered Uranus. So this is the first discovery of a new planet. Now, we've discovered moons and rings, but this is a whole new planet orbiting the sun. At first he thought it was a comet. He thought he found a comet, but after he tracked it for a while, he realized it was in a very long circular orbit around the sun at great distance. And he was very excited and named it Georgium after King George. He's no dummy. He's trying to win some political favor here. And this is the same King George that we fought against for our independence and formed our democracy. But he named the planet Georgium. And nowadays we have an international union. It's called the International Astronomical Union that is tasked with naming objects and classifying objects. I mean, none of it's perfect. Classification is a human enterprise, as we'll talk about in a little bit. But they're tasked with figuring out what is what and what we call it all. But back then, we didn't have an international version. Each country had its own version. So Britain called this Georgium for a while, and the French and the Americans and others, we didn't like that, of course. So we named it Uranus, keeping in, that's in keeping with the naming convention of the other planets named after Greek and Roman gods. And that's what stuck. So it's Uranus. But the king was sufficiently pleased that he funded a large telescope effort. So as I go through this history, I'm also going to show you the biggest telescope of the day. Here's just a modern day picture of Uranus. If you're in the lab course, you took a picture like this and you saw some medium-sized moons. Now, Herschel discovered Uranus using a small telescope. You don't need a big telescope, but because of his discovery, he was able to build a big telescope. And this is called the 40-foot. I think it's the only telescope named for the length of the tube. Most telescopes are named for the size of the mirror or lens. The mirror at the base of this is 49.5 inches. It's almost a 50-inch telescope. But historically, it's named for the length of the tube, so it's called the 40-foot. And it's quite a contraption here. You see all this rigging. They can pull the tube up on this pulley system to change how high in the sky it's looking. And it's on a rotating base with wheels and a track, pulled by horses, if I recall. And so they can point it anywhere in the sky, but it's a slow, cumbersome process. You basically figure out where your object's going to be, you point it to that area, and you wait. And then your object moves through your field of view. You're not trying to track it in the sky in real time. That would be too cumbersome with this apparatus and horses and whatnot. But a large telescope. And it began its operations in 1789 and ran all the way through 1839. Largest scope in the world then. And it was used to discover the remaining medium-sized moons of Saturn and the medium-sized moons of newly discovered Uranus. And the moons of Uranus, they're all named, for the most part, most of them anyway, are named after Shakespearean characters. So astronomers like their naming conventions. I think features on Mars around where the rovers land, or the first rover landed, were named after cartoon characters. It's always random stuff. Okay, that's the 18th century. And then moving into the 19th century, we have my favorite character in the history of astronomy, or at least he became my favorite character after I saw his picture here. I don't know if his head is actually shaped that way or if it's just he hired a bad artist. And yeah, but I like to, I don't know. I think it's probably a decent artist and he just had a lumpy head, but maybe that's mean of me. I don't know. But this is Giuseppe Piazzi, and he's my favorite not just because of his poor portrait, but because of his sad story. He discovered a planet and it was taken away from him. And this story will have analogs when we talk about Pluto, which has just in modern days has gone through a similar process. But don't worry, Giuseppe's story has kind of a happy ending as well. Anyway, Giuseppe Piazzi, he's looking for a planet between Mars and Jupiter. If you look at the progression of the planets, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, known at this point in time, the distance between them is increasing in a very regular way. They're not evenly spaced, but the increase is very predictable. You can almost model it with a geometric sequence, and which is kind of rare. We've now seen thousands of systems of planets out there in the past decade or two, and they tend to be a little bit more scatterbrained. Ours seems to be pretty regular. Anyway, if you believe this geometric sequence, there should be an object between Mars and Jupiter. Something's missing according to the sequence. So he was convinced something had to be there, and he's looking for an object kind of at that distance from the sun. He knew it would have to be faint, else it would have been discovered already. So it would be a very small body. But he was looking, and by 1801, he discovered Ceres, C-E-R-E-S. If you're in the lab course, you took a picture. It's the largest thing in the asteroid belt. This is a picture taken with the Hubble Space Telescope, which is super powerful. And you can see how blurry it is. That tells you how small this thing is. From the scale there, you can see it's maybe a little bit over 1,000 kilometers across, not big at all. And to him, it's just a point of light. He can't see even this much detail. But he tracked it, figured out its orbit, and using Kepler's third law, you can figure out its distance from the sun. And it was right where he thought it would be. And so he discovered a planet. Very exciting. And then over the next few decades, 70 more planets were discovered between Mars and Jupiter. And nowadays we just call this the asteroid belt, but each world as it was discovered and verified to be orbiting the sun, they called it a planet. And just think of the poor school kids back then having to learn the names of the planets. You all had to learn 9 and then they changed it to 8. But they had to learn like 70. It was just really sad for them. And so, again, there wasn't an international astronomical union. There were a bunch of smaller ones, national ones, but they all said, okay, forget it. We're going to demote all of these. None of them are planets. And so Giuseppe Piazzi lost his planet, as did everyone else who thought they had one. And they called them asteroids. Astra meaning star, oid meaning like, so star-like. They just appear as points. They're so small they appear as points. If you're in the lab course, you took pictures of even Uranus and Neptune. You can tell they're not star-like, they're extended. But these just look like points of light. So demoted. Giuseppe lost his planet, but we'll come back to him. Now also in the 19th century, this was the grand era of discovering planetary moons. And many have been discovered already, the large ones and medium-sized ones, but there are many, many more small ones, and they started picking these off like crazy. And this figure just shows, we have the 7 large moons. Here's ours. Here's Io, Europa, Ganymede, Callisto. Here's Titan. And we haven't gotten to Neptune yet, but here's its large moon, Triton. Then you have the medium-sized moons pictured here, and then lots of smaller moons as well. Not pictured here, but they were discovered then and continued to be discovered to the present day. I haven't updated my numbers, I think for a year or two, but last time I updated the numbers on my notes here, Jupiter was up to 79, Saturn was up to 82, Uranus was up to 27, and Neptune was up to 14 moons. And part of the issue is we've never defined a lower limit for how big an object has to be a moon. If we discover anything going around the planet we called a moon. So we keep finding smaller and smaller things, particularly as we journey out there with spacecraft and get really close, or build things like the Hubble or the next generation version of the Hubble, the Webb that's coming. I'm sure we'll discover yet more moons. But it really took off here in the 19th century. Now by mid-19th century, 1846, we discovered Neptune, the last planet, even though for a while there we thought Pluto was a planet too. That would come later, that's next. But 1846, we have the discovery of Neptune. And this one was discovered in a completely different way. It was discovered mathematically. It was predicted instead of just found by searching the skies. And that's because Uranus had been discovered and people were watching it and tracking its orbit. And its orbit was not a perfect ellipse going around the sun. It was a little bit distorted, which means something was tugging on it. Something happened to be nearby, tugging on it. And so they calculated, well, actually these two people calculated, it has to be coming from this part of the sky over here and be about this massive to tug it that much. And so who we have here, we have Adams on the left, he's a British astronomer, and Leverrier on the right, he's French. And they both get credit, though Leverrier should probably get more credit. Leverrier said it's going to be coming from this part of the sky, pretty precise, and stood by his guns there. Adams, he kind of waffled. He said, it's kind of coming from this larger part of the sky, and I'm not really sure. And no, I'd take it back. No, yes, maybe, that kind of thing. And no one followed up Adams' recommendation, but they did follow up Leverrier's, and they found Neptune right where it was supposed to be. Here's a modern day picture. And a week later, they discovered Triton, the large moon of Neptune. You can see it in this picture. If you're in the lab course, you've seen this. And after which Adams, went on a spin campaign saying, I did this too. And so history gives him credit, probably more than he deserves. Now, a fun little side note is Galileo. Back in 1609, when he was drawing the pictures of the moons going around Jupiter, and he also drew some of the background stars, one of those background points of light was Neptune. And he watched for many, many days and weeks. And of course, Jupiter is moving through the sky, so after a couple of days, you're watching other stars. But he monitored Neptune for at least a few days. And it just happened to be entering retrograde. So it was stopping its prograde motion. It hadn't begun its retrograde motion. It was standing still. So he just thought it was another star. If it wasn't at that unique time, he would have seen it moving and would have discovered Neptune all the way back in 1609, in addition to everything else he discovered, which would have been just super extraordinary. He almost got it, but not quite. So it went to Adams and Leverrier in 1846. Now, large telescopes of the day. The next big one was it's called the Leviathan, a Parsonstown, built in the Irish countryside. It's a 72-inch mirror, so a larger mirror at the bottom of this tube. And the tube is also on a crank system where they can crank it up to any particular elevation, but it's not on a rotating base. It points on the meridian, so you wait for something to get as high in the sky as it's going to get, then you crank the telescope to that position, or actually you probably move it to that position beforehand, and so you can just watch it drift through. It's what we call a transit telescope. You're just watching it transit overhead. But largest of the day, the 40-foot, its operations ended in 1839. The Leviathan began in 1845, so there's about a 6-year gap, and they ran this till about 1920. And the next biggest one was built in 1917. So this had a pretty long run of it, and it's still there. I don't think they use it, but you can go there and see it in Parsonstown, I guess it is. The Earl of Ross built it. Okay. This brings us up to the 20th century, which is all the farther I got in the other class. And so I probably won't go there, but the first person we'll talk about is Clyde Tombaugh, discoverer of Pluto. We'll pick up here next time. That's it for today, and I'll stick around for questions.
Thank you.
Thank you.
My pleasure.
Thank you.
Where can I find the videos that you want us to watch?
Oh yeah, they're on the YouTube site. So youtube.com/introastro. And if you go to the bottom, there's a playlist. It says something like Astro 101 COVID edition. And there's actually a playlist for each lesson.
So scroll down to the bottom.
Yeah, I'll actually bring it up here for you. Oops.
The Solar System COVID edition, is that what you're talking about?
Yep. And so under lesson 4, oops, one second. I'll just pull up the full list. So the ones I'm recording have a date after it. And the ones that I'm not getting to, they say Astro 101. They're older videos that I've stuck there. These 2 are optional.
Can you repeat that?
Yeah, the ones I'm recording, like right now, they'll have a date at the end. It's like the topics we covered and a date. And then the ones that I'm supplementing with, they start out by saying Astro 101 : and these first 2 here for lesson 4, they're optional. I said for when we talked about radio astronomy, if you want to learn more about the history of radio telescopes, you can watch these 2. But here's radio interferometers and here's space-based telescopes.
So those last 2 you would highly recommend to watch.
Yeah, yeah.
And is that going to help? Because I didn't understand the first warm-up question. I didn't understand it. Would watching those videos help?
Yeah, it should. We talked about interferometers very briefly in class, so near the end of this lecture. But if you watch this, it will help. It will explain what an interferometer is and how it works.
Okay, and my one last question is, can you repeat the first warm-up question from today?
Yeah.
I just wanted to write it down.
You can also screen capture. And of course, I post all of these shortly before the exam in the WebAssign announcement area. There it is.
Thank you. It resolves. Okay, because this is like, that was similar to some of the homework from last week, but it was like a little more complicated.
Yep. It's a resolving power calculation. This is lesson 4, just final questions from lesson 4.
Oh, this is still a lesson 4 warm-up question?
Yeah, the warm-up questions that we did today were lesson 4, the 2 parts that, the 2 videos I asked you to watch. That's what they're from.
Okay. Okay, thank you.
Sure.
Have a good one.
You too.
I just had a quick question. In that picture with what is it? All the large objects in the asteroid belt that were found back then, was that a second Europa or was that a Europa for scale?
Let me pull it up. I think there's an asteroid called Europa as well. Let me see.
Does that conflict ever, or is it like, how do they specify if they're ever talking about that?
Yeah, that could be confusing. Like in the lab course, if you're using Skynet and you type in Europa, it'll probably give you 2 options. One will say Europa asteroid and the other will say Europa moon.
Yeah, I think I actually have done that before, and I think it happens with a couple of other objects as well.
Yeah, there's like Saturn the planet, but there's a Saturn nebula.
Yeah.
And other things as well.
All right, I was just wondering. Okay, thank you.
Sure.